Welcome to a video lecture of EE351. In this video lecture, I am going to discuss another example of DC to DC converter. So the specifications of a boost converter is given below, and you need to calculate the inductance of the inductor and the capacitance of input and output capacitors. So that's the question. So we will work out this example. So if we draw the schematic diagram of the boost converter, this is the diagram L, Q, D, C out, C in, we have V in, V out. So this is I inductors. So first we will look at the input output relationship. So V out over V in is equals to 1 over 1 minus D. So from this we would get 1 minus D is equals to V in over V out. This will give D as 1 minus V in over V out. So we can calculate the duty ratio for this example. So V in is 24 and V out is 60. So when you calculate, you will get 1 minus 24 divided by 60. You would get 0.6 as the duty ratio. Now first we need to calculate the inductance. For that we could consider the voltage drop across the inductor and current flowing through the inductor. So the inductance, so when the switch is closed, the input voltage would be 24 volts, that this is equals to V in, and during the turn off time what you would have is this is TS, T on. Here you would have V in minus V out, so it would be equals to minus 36 volts in this case. So during this time we would have the current flowing through the inductor by inductor, so it's going to linearly increase and it is going to increase. So this is the inductor current. So I will consider the on state. From that we could write an equation for L. So the voltage is V in and time is T on, so we have D over S delta I inductance. So here my inductance is delta I inductance. So we know V in, we have calculated T, we need to find what is delta I inductance. So we could calculate I in, the input current. It would be P in divided by V in. So input power is 150, input voltage is 24. This would give me the answer as 150 divided by 24 is equals to 6.25. So the input current is equals to 2.65 amperes. So we could calculate the delta I inductance, which would be equals to 20% of the I inductance average. So I inductance average is equals to I in, because when we consider the input current and inductor current. Therefore, this would be equals to 0.2 times 6.25. It's going to come as 1.25. Yes. So from this, you could find out L to be, so V in is 24, duty ratio is 0.6, divided by switching frequency is 20 kilohertz, multiplied by delta I inductance is 1.25. So this in result 24 into 0.6 divide by 20 into E3 times 1.25. So the answer is 5.76 into 10 to the minus 4 henries, which will be 576 microhenries. So that is the inductance of the uh, inductor. Then we need to calculate what would be the capacitances of the input and output capacitor. So first we will consider the input node. So what we have is, we have the input capacitor C in, we have V in, I in, and I inductance. So if we plot the currents, we would have this kind of a waveform for the inductor current. Then should be I in. So you have the this area, this delta Q in, which has to be stored in the capacitor. So here you have TS, this point you have T on. Now you could calculate delta Q in. So delta Q in is equals to half delta I inductance by 2 times Ts by 2 would be equals to delta I inductance over 8 Fs. Then we could write C in to be equals to delta Q in over delta V in. So this will result delta I inductance divided by 8 Fs. So that is the delta Q in. Delta V in we would write as V in times delta V in over V in. So we could do the calculations. The delta I inductance is 1.25. 1.25, 8, switching frequency is 20 kilohertz, the in is 24, and the ripple is ripple is 2%, which will give 0.02. So now we can do the calculation. 1.25 divided by 8 into 20 into E3 into 24 into 0.02 is going to be equals to 1.63 into 10 to the minus 5 farads, which will be equals to 16.3 microfarad. So that's the input capacitors. Then we can look at the output capacitance. So we will consider the output node. So we have the C out, V out, you have the I out, and diode current. So you can plot the waveforms. So if we take the diode current, it would be 0 during the turn on time, and in the next turn off time it would be equals to the inductor current. So we have this kind of waveform TS and T on. Then if we plot the I in, I out, you would have a constant current. So now I can consider this area delta Q out. So that amount of charge need to be stored in the capacitor. So this would be equals to I out times T on, I out dTs is equals to I out d over Fs. So therefore we could write C out as delta Q out over delta V out. So delta Q out is I out d over Fs. Then we could write V out over delta V out over V out. So that's the input output capacitance. So we need to calculate what would be the output current. So we will assume P in equals P out. Therefore we can calculate I out as P out over V out. So P is 150 and V out is 60. So we would have 2.5 amperes as the output current. Now you can calculate the capacitance. 2.5 into 0.6 divided by 20 into 10 to the power 3. The voltage is 60 and the ripple is 0.02. So if you go back one, output voltage is 60, ripple is 2%, power is 150. So we have 150 divided by 60. We have this equation. 2.5 into 0.6 divided by 20 into E3 into 60.02, 6.25 into 10 to the minus 5 farads, or 62.5 microfarads. So that would be the output capacitance of the uh, converter. So in this example we considered a boost converter and we calculated the inductance and the input capacitance of the input and output capacitors for the given specifications. So with that I will conclude this video lecture. Thank you.